So I'm going to get into a meatier part of the talk here. I want to spend a good bit of time talking about this characterization tool called Darshan.
All right.
Oh, hey.
Before you get into the next section, I have a question on choosing the stripe count and stripe size. I see that you mentioned that. Is it okay if I ask the question now, or can you do it later?
This is great. Yeah, thanks for asking the question. I can't see the Zoom chat as I share one screen and use my laptop. So if people are talking on Zoom, I'll only see that at the break. And so speaking up is great. I love it. Thanks.
Okay. So I see that you mentioned that we use all the OSTs. But for example, if I have a given data size that each rank is writing or reading, do you have like a guideline on how I should choose my stripe count and stripe size? For example, if I have like 4096 ranks on 138 nodes on data, and each rank is writing 4 megabytes of data. So what should be my stripe size? What should be my stripe count? I want the maximum bandwidth possible. Is that like a formula you have or a guideline?
So, right, repeating the question or rephrasing the question, what is the ideal stripe size and stripe count? And I got to say that actually can be a little bit tricky to come up with. I would say that the curves, let me get back here a little bit on the curves. The performance curves are, they're so steep at the low end of stripes and so flattened off at the higher size that I think the stripe count, anything higher than 30 or 40 or more stripes is going to be pretty good, and changing that will get you some gains, but the most order of magnitude gains will be just using more than one. In terms of stripe count, yeah, stripe count is definitely the stripe size. I have some numbers about that later on. We talk about that in the MPIO section after the break. But yes, there is a ideal size when talking to the file system, and it's hard to say the best number, but there are definitely some good numbers. And using libraries like MPIO or other libraries can help you get that number, that right access size, without worrying too much about it at the application level. So yeah, I would say that there are definitely bad sizes. If you wrote 6 bytes at a time, that'd be terrible performance. If you write very, very large accesses, then it'll get broken up into a smaller access size anyway. But when I say smaller, I mean a megabyte or so like that. I think those are usually the good numbers for most file systems.
So for this plot, could you tell me what is the data size that you're using? Are you using a small data or using a large data to get this plot?
Yeah, each client here is writing 1 megabyte. Each client's writing 64 megabytes, and I do a few iterations. It's a 64 megabyte block size, 64 megabyte transfer size, no segment counts. But there are a few iterations to sort of make sure I can report these error bars. And so you can see, for example, the reading back here at the highest stripe count has some pretty, there was one of these 5 results was just terrible performance. I'm not exactly sure why that is. At smaller stripe counts, that was not the case. But I just call it like I see it. And so yeah, this was a fixed access size, varying the number of stripe counts. And I have another experiment in a few slides after the break where there'll be what you can see for a fixed number of clients, varying the access size. It ends up being a big mess. You're right, because one, the error bars are enormous, and 2, the file system is other people are using it, so it's hard to know what the best answer is. But it's really hard to speak authoritatively about one block size number and one stripe size. But I can say, broadly speaking, larger sizes are going to be better if you can do it, and more stripes counts are better if your data size is larger than a few megabytes.
Thanks.
Sure. Okay. Any other questions about the file system side of things? We'll move on to the next to Darshan here a little bit. And we talked a little bit about this. Like the challenge of benchmarking I/O and understanding the I/O is sort of like we just said this question. Because the resource is shared, we may get some pretty variable results. When we measure the performance of the L1 cache, we can run a tight compute loop and we'll get an answer, and the error bars on that answer will be pretty small. No one else is using the L1 cache on our node when we allocate it from a compute system, but that's not the case for the storage systems. A lot of CPU profilers, when we try to apply them to, a lot of CPU-oriented profilers, when we apply them to storage, it doesn't quite make sense. How many instructions was this write system call? Well, there were instructions. We posted some instructions. The CPU scheduled those instructions, but most of the time, the code itself is sleeping while the network does the storage, while the remote end does the storage and responds back. And so a sampling-based profiler may not see those write calls, and that's been a problem sometimes. So instead, we try to use this tool called Darshan to characterize the I/O. And we characterize the I/O a couple different ways, mostly through data structures that tell us what's happening at the I/O level, with some timing and benchmarking related kind of information. But the most important part that Darshan tells us is sort of the access pattern. Is this application being friendly to the file system, or can we do something to make that better? So, as I mentioned earlier in our talk, we've got the software stack, and there are a lot of different layers all contributing to that performance. And so when we try to characterize the I/O, we want to know something that's happening at the file system level. We want to know any libraries that are involved. How are they seeing the data? Are they transforming the data in any way? And we also want to sort of keep the overhead down so that this characterization can be running all the time. We don't want to have to run the experiment one time and then come back later and add the instrumentation, because then we've lost an opportunity to learn how the application is behaving at that moment. So we have this tool called Darshan. Darshan is a library that intercepts I/O calls. Either it's preloaded or it wraps the library calls if it's static, which is a more rare case these days, and records into a modular file information about different levels of the software stack. So your application starts up, Darshan sneaks in there, and when you open a file, a Darshan counter fires off to count this many open files. As you write data, Darshan stores in memory a little bit of information about that write, the size of the write and when it started. And then after collecting all this information, how many reads you did, how many writes you did, then it closes the file closes part of the information too. Maybe it opens 1,000 files or 1,000,000 files or however many files. At MPI finalize, though, that's when we collect all the data and write it out to storage. Again, and then with recent versions of MPI, you can ask recent versions of Darshan, you can ask it to do not just MPI applications, but you can ask it to do non-MPI applications too. And so we've got a few examples of that. I don't think I have too many in this talk, but as you can imagine, code that is a workflow-oriented code isn't doing MPI, maybe using MPI to dispatch tasks, but each task is not an MPI application. We have ways of Darshan can request that to trace those and then log it out. Okay, well, great, but I made the assertion that Darshan is going to be low overhead and this is some older data, but we do these performance regressions from time to time, and it still holds true today. The application that is without Darshan or has Darshan, we try to keep these really small error bars here. Maybe there's a small delay and it's very synthetic, writing lots of data. benchmark. But in terms of percentages, it's quite small. And we're able to show facilities this information and convince them that it's okay to have Darshan on by default. So like I said, this is an older version, but we still do these tests sometimes. And we did run into a little bit of time here. We did run into a fun case where, I mean, fun is the wrong word. There was an application that was using some standard IO calls, the F write instead of write, and these are buffered in a way that the application doesn't see a problem here. It just writes 4 bytes at a time. The buffering takes care of things and then dispatches to the file system once the buffer is full. But timing each one of those 4 bytes on a specific platform, there was one platform that had very slow timers. And so it was one case where Darshan overhead was enormous. And so we spent a little bit of time trying to figure out why, and we found some timers were very slow on the system. We used alternate timers and then got those numbers back down. So we're very mindful of the overhead of Darshan here. And again, like I said, we defer everything to runtime, to finalize time. Is that going to make things expensive? Well, no, the larger files, yeah, there's a few seconds to write out some data, but you know, we feel like a couple seconds at the end, as the number of files are used, maybe there's a look as you use sorry, let me step back here. On the left here, if you use a single file, the overhead is pretty much fixed. No matter how many clients are working on this file, Darshan will write the data out for that one file in a fairly constant amount of time, because the data is bounded. The histograms and the timers are all fixed data structures, and so in this other graph on the right, there's one file per process. So with more files, there is more data to write out, but we're not seeing exponential curve up to the moon. It's just sort of linearly, it takes a little bit of time to write out more data. More data means more time to the file system. Okay. So again, we assert that sites should keep Darshan on all the time. Sites believe us, and they've deployed it over time in some sites and quite a few places, and it's borne out to be pretty true. There are a couple weird cases where applications turn off Darshan because it's getting in the way. We try to fix those and learn from those instances. But you might log into a system and see, if you do a module list, you might find Darshan already part of your module environment along with the MPI and other things. And then now on some systems like Polaris or NERSC Perlmutter, you have to opt in to Darshan. You have to load it up. It's still there on the system. It's just not there by default. And in the worst case, the dependencies on Darshan are an MPI library, and you optionally use HDF5 or an SDF instrumentation. You may need a few other libraries for that, but it's not a very esoteric build system. We build it all the time in user space when we're brand new to a new system. Okay. And so if it's in your environment, getting access to Darshan is just a matter of compiling your code. And if you look for the library, you'll find that it gets in there in part of your library stack automatically. And so you can run the code and you don't have to ask for anything. You just run it, and if Darshan is part of your application, it'll create a log file for you, and then we can look at the log file. Where is that log file? Well, if it's been part of a site installation, there'll be a log path. You can ask the Darshan config tool to tell you. In this case, over on the parallel file system, accessible to everybody, there's a bunch of logs. They're stored by year, month, and day, and then there's kind of a fairly long name which encodes a bunch of information: the date it was created, the job ID, some information about the application and the user, and there's more stuff in the file itself. The file name is just trying to make it unique as possible, so we don't have to worry about collisions. If we had S. Snyder file for every Darshan log, it would step on each other's toes, and you would never have this archive of old runs. Like I said, you can build it through SPAC, you can build it through source, and you load it up. And then, so let's get this one. So there's a couple different ways. We have these logs now. We instrumented our code, we ran the code, it had no overhead or very little overhead, negligible overhead. We got a log file. Now what do we do with it? At the very simplest way, we can decode the log file with this Darshan parser code and get the text-based information out of the file. It's a lot of information, and it can be a little overwhelming if you're not used to it. If you know exactly what you're looking for, like I want to know how many bytes were written by every file in this experiment, you can do some shell scripting and grab it out and get a quick sketch of what's happening. And so that's been a pretty effective way of getting data. Maybe you just want to know you want to quickly iterate on a solution here. Well, we also have some tools inside the Darshan distribution that can generate these reports. This is an older legacy report. We've got a newer version I'll talk about in the next slide, but the information is the same in both the reports. It's just presented a little bit differently. We have on this legacy report, the most important things to me are the access sizes for both POSIX and MPI-IO. We can see that this simple test case that we ran didn't really do much to change the access pattern. It was a bunch of fairly small writes, and the MPI-IO layer didn't transform them down to the POSIX layer. We can see a whole bunch of seek calls and MPI write calls versus POSIX calls. A collection of access sizes here, a whole bunch of 66K writes. And so this quick snapshot of what the application is doing can tell us things like, okay, hey, I spent 40% of my time in IO. I bet I can do better than that. If this graph was down at the 5% range, we might say that's as good as we can get. We'll focus on tuning out the CPU for a little bit and worry about IO later. There's an effort to kind of freshen up that report with a Python-based report. You can run this report and get a web page now, an HTML page, and you can look at it in your web browser or share with somebody else through a link and get the same information presented. Well, not exactly the same information, but some of that information plus extra stuff displayed in this new job summary. We'll talk about all these details in the next few slides. So we have two audiences with Darshan. One, the individual who's looking at these reports and trying to understand their application, but also we want operators and sites to look at these Darshan logs and be able to say something about the application workload as a whole. How many jobs on this system are small parallel jobs, small serial jobs? How many jobs are really large and quite big? Well, it was harder to answer that question from an IO standpoint until we had these Darshan logs augmenting information about every job that ran, right? You can ask your job scheduler with the right magic. I'm not sure exactly what it is, but you could, I'm pretty sure you can ask the job, how many jobs ask for 1,000 nodes or more, or 200 nodes or more. And the job schedule will tell you I allocated 100 jobs last month that were 200 nodes or more. But that job scheduler doesn't know how much IO happened in those jobs. We need a little extra information, like Darshan, to get there. Okay, so the fun thing to do with Darshan logs is being able to go through them and talk about with users if there's any surprises. And so, for example, operators have consultants and help desk staff that works with users to help them understand why they're getting bad performance. The user comes in, asks someone, "Hey, why is my performance poor?" I tell you, I promise you, I'm only writing this header one time. Well, Darshan will tell you something else is going on, right? in this case, here's a access size that says, okay, well, there was a bit of large accesses here, but here 4,000 times this 40K header was accessed 512 times, but you only have 128 files here. What's going on? Well, it turns out the user dug around a little bit and we had a bug in there. It should have only been the header is open 4 times more than it was expected to be. So sometimes the users unwittingly will not tell you the truth when they try to talk about their application. They have an understanding of what's happening. Darshan helps sort out the understanding from what's actually happening, and that's been really helpful in quite a few cases. Okay. We'll talk later in the day about MPIO and HDF5 and what's the best way to use those things. But in this case, here's a code that was using a whole bunch of time in MPIO in IO performance. And we thought, well, hey, look, why are my access sizes so small and so large here? I did all the things that you told me to use. The performance is quite poor. All that was required here was a sort of misunderstanding of what happened with HDF5 and these requests. And we'll talk about that again. I'm forward referencing a few of the tricks that we have here, but when you see this result, we look at what's happening is the user told HDF5 it was data in a certain type, a double instead of float, or for example, and the data on disk was a different type. Maybe it was single precision versus double precision, whatever the mismatch is. The point is, when HDF5 sees that mismatch, it turns off some optimizations because it's like, whoa, I got to be careful here. And so, as a result, some important optimizations weren't being used. But when we fix that mismatch, now IO time is a fraction of what it was before. 5%. The conversions, the data conversions we expect are happening now, and megabyte transfers instead of kilobyte transfers, and 40 times faster code. Sometimes we'll look at these graphs and we'll see, this file is 8 gigabytes large. How are you reading 500 terabytes out of that file? Well, some applications are set up to reread data over and over again, but that would be a pretty good case for caching or a local buffer, something to, if this data is hot data that you need to keep referring to, we probably need to pull it closer to the computation and not keep reading it from the parallel file system. We talked a little bit about, I'll talk more about IO transformations. We talked over the Q&A, small transfer size versus big transfer sizes. So in this case, if you have lots and lots of 100-byte writes, in this case, there was millions of writes, billions of writes, wow, to a shared file. That's going to be awful performance. It just requires a small tweak to adjust that. Maybe a collective IO optimization, or somehow aggregating or coalescing that IO at the application level, whatever makes sense, to get larger request sizes out to the storage system. And then sometimes the metadata cost is surprisingly high. In this case, this blue bar here is POSIX metadata. It turns out that was so high because there's just lots of open calls and lots of stat calls here too. And you got to open the file. You can't do anything without opening the file, but statting a file ends up being pretty expensive at scale. And why is that? Well, when we ask a parallel file system, how big is this file? And when we stat the file, one of the things we're doing is asking not just does this file exist, but we get back information about how big that file is. But remember, a parallel file system has multiple servers all handling pieces of that data. So many times a stat call requires the file system to pause, to collect information from all those servers, and then report the result back. And so that can be a surprising case of poor performance. Stat, for example, shows up in LS. When you list the contents of a directory, you're statting each one of those files, and that can really perturb performance for everybody else that's using the file system. Okay. I want to see here. Now this graph here is not a stock part of Darshan, but what different sites have done is taken these Darshan logs and done things like inject them into an SQL database so they can do queries across all the files and figure out what's going on. So in this case, you can do a report at NERSC. You can do this report and say, who's running out of the home directory? And on these systems, often the home directory is configured much differently. It's serial, it's expecting a totally different workload than the parallel file system. So you want to find out who's beating up the home file system. Let's talk to them and have them use a more appropriate file system, for example. And you can imagine, we're not quite there yet, but you can imagine every night some job looks through these logs and says, oh, hey, I found a couple of users I need to talk to tomorrow. And we can have them, we can identify their problem, fix it before they even are aware they have a problem. And that makes everybody happy. Yeah. So let's go back down here. We went look at, let's go back to Darshan and about what we can do to instrument each one of the different levels of the IO stack, right? We talked about the challenges about what's happening at the file system layer, the MPIO layer, and so on as we go up. And there's a new report that we've created called a heat map. And I think this is a lot of fun, although they're quite dense. So I'm gonna take a little bit of time to talk about them. So this heat map is kind of, you can think of it as a super duper histogram. I don't know, maybe that's the wrong phrase to use, but as I said, Darshan isn't going to try to capture every single write operation. Well, sorry, let me step back a little bit. Darshan showed up around 2009, and we really focused on dialing down the amount of memory that Darshan was collecting. But over time, we wanted to know a little bit more about access patterns. And so how can we talk about the pattern over time in a memory scalable fashion? So one of the things we came up with was this heat map. And I'm speaking entirely of a product. I didn't have any hand in development of it. I love using them and looking at them, but I didn't develop these. My colleagues, Shane Snyder and Phil Carnes and Tyler Reddy over at Los Alamos did all the work on these pieces. Okay, so the heat map, right? We have a row for every MPI rank that's involved in the process. We color these bins based on the intensity of IO. So in this example, you can see sort of phases of light IO, and then at the end of the run, a pretty heavy bit of IO. Each bin is marking a start and stop of an IO operation. So it's getting to be a logging approach, but again, because we're binning based on time, we're losing a little bit of resolution here, of fidelity. This isn't a perfect match of what I was happening, but it's pretty close. And then, okay, right, and then up here we have another histogram of IO in terms of time. So each phase of this IO had an intense phase as everybody worked on IO, and then fewer and fewer processes were doing IO. And then over this last phase, you can see a much higher spike here. Then this vertical histogram is recording on in terms of ranks, which processes did all the IO. In this case, it's quite balanced out. Everybody was part of the IO here. So again, we'll see this heat map show up a couple different cases throughout the day, but it encodes a whole bunch of information. All right.
Rob.
Hey.
Sorry, I missed it. Could you tell me what is the difference between the black bars on the top and the orange bar? I understand the orange bars for the heat map, but what's on the black on the top?
Yeah, absolutely. That's definitely worth repeating because while the orange and red bars, the color indicates intensity of IO for that specific operation, with light colors, yellows being small amounts of of data, and dark reds being more data. Up on top, we're looking at data in terms of if we just squished the whole graph down into a time graph and not by rank, at which time was the most IO happening. And so now if this is a okay, here the important part here is 200 time bins. So the data structure allocates some number of these a resolution of this. So we know this report is going to show up on a web page with about 600 pixels or 1,000 pixels. So we give each bin a few pixels. There's 200 of these time slices, and then you look at how much IO happened across all the ranks in each of those 200 bins. And so the peak here is 1, 2, 3, 4 peaks, suggests that these IO phases were really intense, and then as the bulk of the IO happened, there'd be some stragglers that would write out IO a little bit more slowly than other processes in this first region of the data. I'm not entirely sure what workload generated this graph, but the answer to your question, the horizontal histogram is showing in time which seconds of time had the most IO happening, and then the vertical histogram is showing which ranks, independent of time, which ranks did the most IO. And in this case, every rank did the same amount of IO. So it's harder to see the differences here, but I'll show you an example from maybe after the break about that.
Rob, I just wanted a clarification on this one more time. So the bars are the most IO from the group of ranks that's happening, right? Each bar, like that's the most IO from the 30 ranks.
The vertical bars along the right-hand side of the heat map show which MPI ranks did the most IO. Yes.
Thank you.
Great. All right. Moving on. We can do tracing and studying the higher level IO libraries too. So here, this report didn't come from a Darshan report. We pulled it out of the logs and massaged it in matplotlib, but you can collect all the timers and information that's in the Darshan log and say something like, among all the processes, with this, so here, let's take this MaxCO benchmark. It uses HDF5, and if we use independent IO, we're spending a lot of time in POSIX, a little bit of time in the HDF5 library as we keep issuing requests, but the application isn't really doing all that much. It's got its IO kernel, the computational kernel that it's modeling here. And as if we turn on collective IO, that red part, the application part, doesn't change. Of course, that application is going to do a few seconds of simulated computation, and then now the MPIO layer is doing more work. In this case, collective IO optimization. We'll talk about the kind of collective IO optimizations that happen after the break. But the trade-off is by doing a little bit more work in the MPIO layer, there's almost no POSIX IO time here, no HDF5 time happening here, because we've massaged the request in such a way that the file system is going to handle it and write that as fast as possible. All right. We're going to let's make it better. So, are there any other questions about Darshan? I'm going to take a small break and rest my voice a little bit here. We'll come back, give everyone a chance to use facilities, whatever they need to do for like 15 minutes, and then we'll come back and talk about some of the more analysis tools we've added to Darshan. But are there any questions about Darshan or Lustre or file systems before we take that break?
Rob, I have a question about the file system in the Lustre part.
Okay.
So I understand that we are running jobs when other users are running, and there'll be contention. But for example, take a system like Polaris. the theoretical bandwidth is 650 gigabytes per second. That's what you say. But how
Yeah.
much should I see? Is it 10? Is it 100? Like, what is normal when other users are using it?
Yeah.
Like, it can be approximate.
No, that's a great, that's the kind of mental model of these file systems that I hope we can develop. That was harder for me to get the answer than I thought. The kind of tuning parameters that were supposed to get a larger fraction of the advertised IO didn't seem to work for me when I was collecting these data. So as you saw from that contiguous benchmark, I was getting 20 gigabytes, maybe 30 or 40 gigabytes in some cases for a shared file access. Single file per process was getting me 200 gigabytes per second, and that seemed to be the fastest I could get from these files. So somewhere between 200 and 20, if you're using about a quarter of the files of the system, seemed to be the right number there. And as we all get better at and more familiar with Polaris and the file system, we should be able to get those numbers higher. But right now, that seems to be where we are.
So sorry, so are you saying 20 or 220?
Yeah, if you use a shared file, kind of the friendliest way to manage that data, I was only able to top out around 20 or 40, maybe top out at 40 gigabytes a second. I think that number is too low. I should be able to get higher than that, but I wasn't able to get higher than that for these benchmarks. If I use a different, less ideal approach where we have every process write its own file, reading and writing would be faster, about 200 gigabytes a second. But then then you have a bunch of files to deal with. And 1,000 files is not terrible, but it's not, we're getting to the point where you're going to start stressing out the metadata server of the file system. And then what do you do with 1,000 or 10,000 files? You've got to get them picked up and taken somewhere in an actual application. So I sort of have a caveat on that 200 gigabyte number. And my goal would be to tell you the magic recipe so that shared file performance matched the file per process performance, but I don't have that magic recipe yet, but I'm going to keep working on it.
Okay, so I did a simple IOR run
Okay.
last week. It's on Grand,
Okay.
the /luster/Grand projects file system. So so both the machines, Theta is connected to Grand and Polaris is connected to the same Grand.
Yes.
And doing a simple IO test, and Polaris is 10 times faster than Theta. Why is that, and how can I answer in my paper? Like, people will ask me this question, right? It's the same Grand system.
Yeah.
I can show you the numbers if you want, but later.
I believe you. I would have to start saying things like on Theta, the KNL nodes are kind of underpowered, and maybe there's some problem with the clients relative to Polaris clients. Maybe they're, yeah. I would. That's interesting. I would like to know more about that. So how about we should talk more about that. I don't know if I can't give you the answer standing here right now, but I would like to hear more about that and figure out more why that is. I am going to spend a little more time talking about some of a new facility we've added to Darshan, because this ability to use all the Python analysis pieces that are out there and apply them to Darshan logs seems to be a very fruitful new area for us, and we're looking forward to seeing what we can figure out with this. So there are two components to this. We've already talked about the user-facing side of it, the new job summary tool, but that's using this PyDarshan log framework. So in the old day, and we still have this piece, you could use a library to pull Darshan records out and work with it at a C level. But if you did the, C programming is I program in C all the time. I use it constantly. It's not the best choice for something like this where you want to rapidly visualize some data. So we worked on this new, again, not me, but my Darshan colleagues worked on this Python log framework so that we can apply Python scripts to Darshan logs and get information. So it's living up on the pip world. You can pip install Darshan and get this working on your laptop or install it as a user on the Polaris machine, like I did in my own home directory. We had this Python-based, this Perl-based script that generated a PDF. Now we use the Python and the summary tool to generate a report that looks a little more modern and has a little more information. So again, walking through, what does the job summary tell us? It records the job ID, the way the job scheduler assigned a number to this job. So we need to go back and if we want to go back and find out more about what was going on at the system level, we can use this job ID to help us figure it out. It tells us about the time the job was running and records the command line, which is pretty helpful to figure out which configuration we were running, for example. And then runtime is useful too. You see, did this change in an IO parameter affect the overall runtime of some science job? Now, again, here's our heat map. We can talk a little bit more about this configuration because what's going on here? We have an MPI-IO heat map on the left-hand side, where we have different phases of IO happening. Three IO benchmark, three MPI-IO calls here. So we can see from the histogram, right, in time, there was these regions of lots of activity happening at the MPI-IO level, and then nothing happening. Then more IO, and then nothing happening. And all the processes are doing some kind of IO at the MPI-IO level. As we'll see in the next section of this talk, when we talk about what MPI-IO does under the hood for you, there's an optimization where only a subset of processes end up writing data to the file. And so only every 10th or 16th process here is actually doing some IO. Time-wise, there's still IO happening, but it's all been sent down to an IO aggregator. And we can see this characteristic of the MPI two-phase optimization kicking in and applying to this workload. It's also helpful to see if you configured your file system right, because in this case, only one process is doing any IO at all. Why aren't all processes working? Well, the MPI library looked at the file had a strike count of 1, and so okay, we'll send all the data to one process because there's no benefit to doing parallel IO to a file that's stored serially. Okay, well so if you were to look at this map in your Darshan report where the MPI-IO does one thing that makes sense to you and then the POSIX layer does not make sense, then you can ask, well, what's going on here? In this case, a very small stripe size. Again, at the HDF, using an HDF5 example, we don't have an HDF5 heat map, but we can infer what's happening from HDF5 down into the MPI-IO layer. And so over here, we've got a bunch of MPI-IO calls, and then it looks like they're not doing any different. They're just calling right down to the POSIX call directly. We'll talk a bit about, again, keep selling this part down the road. But this collective algorithm that uses a small number of processes isn't happening here. And there's a couple different reasons that the HDF5 library, why that might be the case. And we can talk about that in the HDF5 section. We talked a bit about IO costs, right? And again, so whereas in the legacy report, we talked about percentage of runtime, instead, we sort of measured, we leave the non-IO parts blank and just fill in, in this case, there's a bunch of MPI-IO calls and then a little bit of POSIX-IO. There was some work done at these higher level libraries in the software stack, and the IO call here was pretty pretty limited. So that's great. These libraries did the right thing for us. We might talk a bit about how to get these gaps a little bit smaller. Why is there so much MPIO time versus POSIX time? But that's the kind of questions these reports help us ask, and then hopefully investigate more and find the answers. Operation counts is fun because you want to see things like writes are happening. You don't see too many stats. That's good. You know, how many files are being opened, and so you can learn a little bit about the kind of file operations that are happening. Again, with these software stacks, you may not know why there are 100 stat calls, for example. In this case, there weren't 100 stat calls, but you know, maybe there's some surprise stats sitting somewhere in the call. For example, I was looking at a high energy physics code, and before they load a dynamic library, they do a stat of the file to see if it exists. And well, as we talked about this before, stats can get kind of expensive, and so instead they just rework their code to load the library, and if it failed because it didn't exist or wasn't around, or there's some other error, they could then do something in the uncommon case, but they took the stats out of the fast path, and so that was a good change there. Now these histograms are still used in the new. They were so useful in the legacy report that we kept them in the new report. These are simpler histograms than our heat map because they talk about the sizes of those access patterns in a way that you can see quickly and not to decode colors. But between the histogram and the common access size table, where we keep track of the top 4 common access sizes, we're able to say something about how friendly is this workload to the file system. In this case, not too bad. If we saw a bunch of small writes, like we saw earlier in the Darshan talk, we might think about how to change that, how to adjust that. And we'll see more about the effective access sizes in a little bit. There are an ever-growing ecosystem of Darshan tools. I won't talk quite through all of these, but you know, the 2 newest ones here, Dristi and DXT Explorer, come from our colleague Jean-Luc Bez over he's now at Berkeley Lab, and he's been doing all kinds of work with Darshan logs and come up with scripts and tools to help present those Darshan data in novel ways. And we'll see a couple examples of those in the MPIO section. So just to wrap up here with Darshan, I want to make sure everyone's aware that we've got a whole bunch of tools and facilities, resources available so that people can look at not just individual files, but the fun part about this PyDarshan interface is that we can send it across a bunch of different files. And so whereas before, we showed you how some sites load Darshan logs into a database and then do a query. That's still a practical and effective way of looking at a bunch of Darshan logs. But now we can also use these scripts to sweep through logs with simple command line tools that we've written to develop queries that we want to know at that moment without getting a whole database involved and administrators and custom and come up with custom queries and all that. Which again, if you are a database person, that is a fantastic way of getting information out of Darshan. But here's another way of providing that information.